introduction to what is EREAP, why is it cool, why is it significant, and also some background on exploitation and return addresses. Then I'm going to talk about the internals, like how the arithmetic works, and how the emulation core works. And last but definitely not least, Yuji is going to provide a very cool demonstration and some stats on, why EREAP's cool. But first, here's Ryan with the weather.
Good morning. Today, I'm going to kind of give an introduction to the technology that we're going to be demonstrating here. The technology is called EREAP. Specifically, it deals with return addresses. Now, return addresses only have an importance in the context of exploitation. So, although this talk is not really about exploitation, we need to get a couple of terms out of the way here. In the context that we're talking about, an exploit is any attack that will specifically take control of EIP on a processor. These types of attacks can include buffer overflows, format string attacks, function pointer overwrites, basically any type of attack that will give you control over EIP. Now, traditionally, any good attacker is going to use this control over EIP to execute their supplied code. In this context, there becomes an issue of how do I get control over EIP to my supplied code? In this system here, we're considering a return address any way when loaded into EIP will result in executing our return code. If you could imagine for a moment a treasure map where the code that you want to be executed is a big red X, the return address would be the path that wound around to get to that X. You could almost say that exploit marks the spot. Silly jokes aside. Basically, in this talk, as I said, this affects any type of attack that will go out and take control of EIP. In our examples, we're going to primarily be focusing on buffer overflow type attacks simply because they're widely known, they're very simple to explain, and most people by now have a pretty solid understanding of them. So, in that vein, we're going to kind of quick go over this, and I'm going to graphically show kind of where return addresses fit into the whole scenario. So you have a buffer overflow attack where you have a stack buffer and you're copying your data in, and you go right up to EIP and then right over. The point right here that's considered our EIP would be the place where we place our return address. Now, as I said before, any competent attacker will use this to put a payload there and execute our payload. There are several ways that are going on this, and we will go into them here. So, in the past, there have been various types of return addresses that have been given. The most simplistic is a static address that you overwrite the saved EIP with that will point directly into your buffer. This type of attack has found widespread use in many local Unix and even some remote Unix applications due to some specifics in the Unix stack that I'll explain shortly. The determinant on this is that you must know where your buffer, your payload buffer, is going to be located in the process memory space before you operate. This is a sort of unrealistic expectation in a lot of cases, and we'll go into that now here. Basically, traditional Unix stacks start at a predetermined address space at the top of the userland addressable memory space. What this means is that your local Unix Soeder root program, when you start it, the stack's always going to be at the same place. Because you're overflowing at the same place every time you run it, your stack pointer is basically going to look pretty much the same. When you decide to put your buffer in memory, you can look at using a GDB and locate the exact address, plug it into your exploit, and jump directly into your code. In the situation where there is some variance, you can use a technique called NOP sledding, which pads the size of your buffer so that you don't need an exact guess, and just a good scientific guess will get you somewhere in your buffer where your NOP sled, which is basically any type of instruction that will not affect the execution of your actual payload, say an inc EBX, dec EBX pair, can be repeated and slide right into your code. That gives you a little bit of leeway. Now comes the Windows stacks. The Windows stack layout is significantly different from Unix. Primarily, every thread that starts has a dynamically allocated stack. This becomes a problem in that you do not know when or where specifically in the process space the stack that you're going to be attacking is going to be located. There's also the addition of the fact that Windows typically uses several threads within a context of execution, making that shift even more apparent. The final part that really kind of bugs exploiters on using static addresses in Windows stacks is that traditionally the stack will be based at 0x00 something, meaning that there's by default a null in your stack space. Now this can be a real problem, especially when you're talking about doing a traditional string-based buffer overflow. So on the side here, we also have heaps. And heaps are, by definition, blocks are allocated as they're needed, meaning that it's very, very unlikely on both Unix and Windows that you're going to be able to guess before running a program where your heap is. These problems are really going to cause a lot of trouble in using static addresses, and that makes this older technique not nearly as effective in using return addresses as it once was. Some smart attackers realized that by looking at the context section of a debugger, looking at the various registries, or registers rather, and what's in the stack, that you found pointers to your code. For instance, on a successful buffer overflow crash, when EIP points off to somewhere in memory, say 41, 41, 41, 41, you notice that ESP at the point of crash points directly into your code. So the problem becomes, how do I get ESP to execute? We have to load the value in ESP into EIP. That kind of brings us up to the state of the current technology in return addresses. What we have is several different programs out there that are collectively known as like jump finders. They share a lot in common, and there are several different variations that have different codes that they're looking for or different ways of going about it. But in the generic sense, they basically will load either a DLL or a series of DLLs from a process space into memory, or conversely, they will attach to a running process using a debugger and look at the existing memory in this context. The traditional way of doing it is to scan for byte sequences that correspond to various opcodes. Now, these opcodes can do things such as, the three most common, as you can see, are to call into your register. For instance, call ESP. That will change EIP to the value inside of ESP, giving you access to your code. Another is to jump directly to the register. And the final most common would be to push the register onto the stack and then to issue a return, which will load it off of the stack into EIP. There's a lot of really good stuff out there right now to find simple instruction sequences like this across various databases. For instance, the Metasploit return address database. Tracks several Windows DLLs across various service pack versions and can give you, with a couple simple clicks, the ability to find a return address that's appropriate for your context. Now, as you notice, I said across several different service pack levels. This becomes a real problem in the current way of doing return addresses, is that as patch levels on code change, the return addresses no longer become valid. What happens is a vulnerability may exist across several different service packs. However, it becomes very difficult to find a reliable return address that comes across each one of them. To find a return address that is universal across all of them requires sort of either holding on to a piece of code that did not change between versions, or locating a specific address that, when executed, will continuously lead. It may be different code, but it may not be significantly different enough, or that all paths may still actually achieve to the return address. So, in the quest for universal return addresses, I'd like to introduce EEREAP as a new way of achieving this goal. EEREAP is the EI emulating return address purveyor. As its name implies, it is an emulator, and we'll go into that in a little bit more. It's got a lot in common with the current the current harvest of jump finders. The purpose, of course, is to find return addresses. We're hoping to find more than anybody else for a better chance of finding cross-patch level correspondences, giving us more universal offsets. Like many other jump finders, we operate on the context of the crash. If ESP is pointing to your code, we need to know that because that's another way to get to your code. If EBX is pointing to your code -4, that's also very useful. So unlike traditional ESPs, we're not specifically tying ourselves down to one path to the code. Also, very similar to existing systems, we're looking at the real-world example of what's actually loaded into that process. We have a companion tool with EEREAP called psnap that will create a complete dump of the memory space. It can also be ran in a way where it will create specific chosen segments of the memory space. For instance, if you choose to do only code sections that are read-only, which would traditionally map to the DLLs that are loaded. It gives you a lot of flexibility in what areas you're willing to look for a return address in. The main difference between EEREAP and any other solution on the market right now is, of course, that it's an emulator. Much like emulators such as VMware or the Box project, which is an open source x86 emulator, it models the x86 instruction set. We're not actually operating on the processor, but on our model. We introduce some differences that nobody else does, such as non-determinism and abstract memory spaces, which Derek will get into more as he shows the internals. But we have a context which comprises the entire register space. We have a virtual memory system that emulates accesses to and from memory, such as an x86 processor would do. The key point and difference is that we're no longer doing simple byte searches. A jump ESP is a jump ESP is a jump ESP, but searching for it will only find individual instances. If by emulating, we can find any complex code path that will actually take us directly to our code. Basically, the process is using the context, the process snapshot, and user-defined limitations that we call CRAGs, candidate return address generators. we can set up a series of return addresses that are potential candidates, and then emulate through each individual one of those, and find, obviously, once execution, EIP, lands in our target buffer, we are set. The advantages of this methodology over any existing methodology are, we have several. We're not looking for simple instructions. If, for instance, a push ret, and we'll show an example of this soon, is separated, a simple bytecode operation is not going to find it. In our testing, we've set thresholds on the number of instructions that we'll consider an emulation chain up to 100, and we found sequences of up to 91 bytes, or rather 91 instructions that will, when executed, always take you to your target buffer. That will give potentially significant better numbers of results, as well as giving you potentially different quality of results. In addition to this, we will find every simple instruction because it will emulate out to the code port or the code point that we're looking for. Basically, in this situation, we will find within the context of what we have, every viable path to the return address. We do have some exceptions where there are some instructions that we don't emulate, such as like MMX or advanced processor instructions. We kind of stuck to the basic x86 instruction set, but those will be covered in our to-do. They're on the slate. The whole bottom line in this is that we're kind of looking for a bunch of different possibilities. We figured that more choice is better than less choice. And when you can come up with significantly more possibilities, you're going to have more potential matches between Service Pack 1 and Service Pack 2. In this, there's also the possibility of, say you need specifically only ASCII character return addresses. When you have more of them, you have more possibility of actually finding a specific ASCII code or Unicode type of address. And our CRAG section that Derek will explain is the way that we put limitations on that. So in the bottom, we by using non-determinism and trimming execution paths that we can't determine as exact matches to your query, we feel that we're getting real-world results that will trim down all the maybes and if this is set type of situations, giving you just good solid return addresses that will work across the board. By emulating each candidate, we have a potentially theoretically ideal solution with the exception of instructions that aren't set and a definition of our context. Because of the memory space abstraction, we're kind of foregoing the specifics of what's in a stack and where it's located in memory. So there are potential point-in-time return addresses that EEREAP will not find. Those are outside the scope, and because they are point-in-time, they're not going to necessarily be effective from one point to the next. And with that, I would like to pass the torch on here to Derek so he can show you some of the deep, dark secrets in the EEREAP Magical Mystery Tour. Derek?
Cool. So yeah, so as it turns out, EEREAP is a little bit magical and a little bit mysterious, and we're going to try and demystify it here. EEREAP is an Intel 32-bit machine code emulator that supports non-determinism, which again is partially and wholly undefined values, and it also supports abstract memory regions, which is important for memory regions that may move around across multiple executions of a single version of a process. These two advantages are important because, where did I go? These two advantages are important because there are certain factors that are unknowable or unpredictable, and this will allow the user to compensate for them when searching for more return addresses. eReap accepts a state from the user. I'll talk about what I mean by state in the next slide. And it emulates at each candidate return address to figure out which ones host or begin a code path that will lead to your target buffer and which ones won't. Let's see. The basic purpose of eReap, I mean, actually the fundamental purpose is to find every start address that leads to a code path that will lead to your arbitrary code. Oh yeah, I should also mention, CRAG, as Ryan mentioned, is our context return address generator, and it allows the user to further narrow down this list of candidate addresses, both by ranges, like say if there are only certain modules you're interested in looking at, or code sections of those modules, and also character maps. By character maps, I mean for each byte position, each of the 4 byte positions of the return address, you can set a list of characters that are valid. This will allow you to do things like ASCII for the low 3 bytes, and then ASCII plus null for the high byte, alphanumeric, alpha, Unicode, you name it. We'll get to that in a minute. Now the state consists of a process memory snapshot, which is just like a memory dump plus, page permissions and whatnot. It's a pretty simple format. And also a context that specifies which registers and which memory locations contain what data. Rule number 1 is that a path from the registers to the target buffer must exist. And this path can be very indirect. Like, for instance, ESP will hopefully always point onto the stack. So contents of stack memory, for all practical purposes, can be considered a first hop in a way. Also, hard-coded addresses, like if there's a specific, say, variable in a global data section of a DLL, that could also be a first hop if you can find an instruction that will reference that memory. Of course, the context requires user observation to construct. It requires the user to look at the environment of the process at the exact pivotal moment that execution will be transferred. Yuji will demonstrate this, don't worry. And jot down, kind of what things seem to be consistent, what things seem to be kind of variable, and also abstract memory regions like, okay, here is a stack. I can identify this as a stack. I don't always know what it's going to be, but it's stack. If there is a way for eReap to get from the initial context to the target buffer, well, then it's designed to find it, and doesn't do a bad job. Again, Yuji's going to show that. I keep plugging his part because it's, it's pretty cool. So memory regions. As I said, the context defines a memory region, which has to be expressed abstractly because they tend to move around across multiple executions. The kind of cooked up example here is stack and heap. In each of these 3 cases, ESP takes a different value. You notice that the low word is the same because the stack is dynamically allocated whenever the thread is spun. Of course, there's usually 64 kilobyte alignment on the virtual address region that the stack occupies. So that's why that low word looks the same. And what this is indicative of is that ESP is a consistent offset into the stack. The stack moves around, but ESP is always at a specific point in that stack. With like kind of a predictable, instruction sequence and a sane, call stack and compiled code, this should be pretty reliable. I mean, you can get some weird like recursion and whatnot, but basically ESP should be a pretty consistent offset within the stack. The heap, on the other hand, is a complete mess. It is a process-wide shared resource. Blocks are allocated at random and freed at random, and about the only thing you can really count on is 8-byte alignment of the block. Either low digits 8 or 0. You have to, when thinking about heap addresses, you have to take into account that how much work the process has done, how much of a load it's been under, how many blocks it's allocated, how many blocks are still there, as well as certain machine factors, even like what directory is the Windows directory, because the length of the Windows directory, be it Windows or WinNT, will influence the size of heap blocks, say, argv and whatnot, and therefore it can change the entire layout of the heap depending. So for all practical purposes, it's best to just say, this is a heap block I'm interested in. I have no idea where it is, but I know what's in it. And that's the advantage of expressing memory abstractly. Okay, to specify the context itself, The most fundamental element of the context is integers, assigning integers to registers, to memory locations. And integers are all tracked on the bit level to maintain the most possible precision. Each bit could either be 0, 1, or x, and x is not 2, x is undefined. It's either this bit may be 0, this bit may be 1. The emulator is going to try and, stick with both possibilities. This is especially important for E flags, which really has no meaning above the bit level. 1 bit, 1 flag. A flag can be, in this case, 0, 1, or undefined, which has some interesting implications when you start talking about undefined flags. We'll get to that point in a minute as well. Declaring a pointer, because memory regions are defined abstractly, a pointer consists of which memory region and then plus offset into that memory region, just base plus offset. In the case of a pointer into the virtual address space itself, which is a completely numerically defined address space, it starts at 0, it contains the data from the snapshot, the process snapshot. These pointers are also double as integers. If you try and dereference an integer, then it's regarded as a pointer into the virtual address space, unless it's partially undefined, and then that's kind of a messy situation, so we don't deal with that. Trying to dereference an undefined pointer means that you're retrieving memory from an unknown location, maybe causing an access violation, so it's just not a really good idea to try that out. To define a memory region, you specify a size, and then optional attributes, and an optional partially defined value. The size is usually just a reasonable over or underestimate, because you don't always know what the size of the memory region is. You don't want it to be unbounded, because that means that any pointer dereference in that region is going to be valid, because we don't know where it sits in the virtual address space. We don't know what the underlying pages are, what their permissions are, if they even exist. A quick example would be, say, ESP is like stack plus 80 million hex. Obviously, that's an invalid address because the stack's going to be in user land, and that would result in the dereference into kernel land. But when you're talking about an abstract memory region, that information is not available to the emulator. So in that case, it's just best to choose just kind of a ballpark figure for the size. In our example, we'll use like 64K. That may be a little excessive. Okay, secondarily, attributes. There's only a couple. A memory region can either be read-write or read-only. Read-only is useful for one if the underlying memory region is in read-only memory enforced by the paging system. Secondarily, if you have a memory region that contains like your payload code and you want to disregard any code paths that are going to destroy that code, then you can set it to read-only, and then whenever a write occurs to your target buffer region, that code path will be disregarded because it causes the equivalent of an access violation. Speaking of target regions, the other attribute is target. It says, this abstract memory region is somewhere that I want EIP to be. If EIP ever reaches that target buffer, within the size that you've given it, then that emulation thread is a success, and that return address that spawned that whole thing is logged. Memory regions, for greater flexibility, memory regions can be mapped into one another. I mean, one of the core tenets of EREAP is that a memory region is abstract, but sometimes it's useful to map one of them into another. Specifically, this is most useful whenever you have one memory region that has a certain size and set of attributes, and you want to define kind of a sub-region inside of that memory region. For instance, my favorite example is you got your stack memory region, but then you've got your target buffer inside of the stack, just a small region of the stack that you want to mark as target. Obviously, you don't want EIP to just land anywhere in the stack. That's not going to help you. But if it lands in that target buffer, which is inside of the stack, then you definitely want to know about that. And knowing that it's inside of the stack is helpful to the emulation engine because, again, you could get there based off of ESP or something, for instance. If a memory region is mapped into the virtual address space, then, it's assigned a fully defined numerical value. Now you're just talking about a specific concrete region of the virtual address space that has this number to start, it runs for this size, and as a region in the virtual address space, the data from the process snapshot applies. On pointer dereference, any overlapping regions underneath that pointer, their attributes are all checked out. So again, if you have a stack pointer that happens to point into this target buffer region, then you want to check and see if that target attribute is in any region that's in that mapping. We're calling these mappings address space composite, so if I refer to address space composite, that's what I'm talking about. Here's an example context. It'll probably piece it all together. It's probably a little bit burly at first, but really it's just single instructions to the context loader. Just tells it what to do, how to initialize the master context. Hope everybody can see that. I can't, but fortunately I have notes. The first instruction just defines the stack as a memory region. It says, we know that the partial value of the stack, and this partial value is again just to aid the emulation engine. If you're performing pointer arithmetic and you need to resolve a pointer into a single integer value, then this base address, or excuse me, this partial value comes into play. In this case, let's say that we ran the program multiple times, and every time the stack was based at, some number beginning with a null, two zeros in hex. So, that's useful information to hang on to. A quick example of when that would come in handy is if arithmetic was performed on that pointer, and say that would cause a sign flag to be cleared, which is could be useful. There can be conditional jumps that use a sign flag. It's just the more information, the better, and the more accurate the emulation. There's that 64K example size I was talking about. That's that's kind of a ballpark figure. Stack, of course, needs to be read-write. ESP is then declared as a pointer into the stack region, just base plus offset. We're saying that ESP is at stack, wherever stack begins, plus E1000 hex. Now we're going to declare buffer as our target memory region. You can see the target attribute on the end. It's also declared as read-only to keep the code from getting mauled by, say, stack operations, like a bunch of pushes and stuff. We map the buffer into the stack at offset E09C, just a ballpark figure, and give it a size of 128. Next up, we're going to initialize some memory on the stack, saying stack plus E1004 is actually a pointer into our buffer. So what this means, ESP is at E1000. This pointer is at E1004. So if there were, say, a pop and then a ret to occur, then that would land you 8 bytes into our buffer, which would cause emulation in the end and say, hey, this is a good return address. Now we define some registers with, what look like some common values. Hypothetically, this is just taken from running the program multiple times, maybe disassembling to see what's going on in there, and just kind of getting a feel for what these values are, can be expected to be. Let's say EAX is 0. Maybe that's just a function return code. ECX 3FF something, the low bits are undefined. Kind of looks like an integer overflow or something. EBP points into the stack. The memory at EBP points further into the stack. It's kind of a typical linked list of, EBP-based frames. It's pretty typical. ESI points into the stack. The thread information block is just another memory region declared somewhere floating out there. We don't know where our thread's TIB is going to be because this is some kind of multi-threaded example. Of course, it has a size of 4K and it's read-write. Typically they're allocated top-down, so it's 7FF something is the value. And that, again, could come in handy to our emulation engine. Of course, it's also 4K aligned. FS, of course, points to the thread information block. And finally, eFlags is partially defined. Some of these bits you can't change no matter what. The instruction, or the interrupt flag is enabled. This is a user mode application. There's nothing you can do about that. Some of the other bits are always 0, always 1. Those never change. And then we've got the carry flag from right to left. Carry flag, parity flag, and auxiliary carry flag undefined. Maybe some arithmetic's happening before the, we seize control that we can't always be sure what the result of the flags are going to be. Hold on just a second. There we go. Okay, now we're going to talk a little bit about emulation and how that works and how that flows. So the top level outer loop of eReap is uses a CRAG to generate candidate return addresses. For each address, we start the emulation with a fresh copy of the context structure and just tell it to go emulate. The context structure is initialized to just default values, and then it's loaded up from the by the context loader based on what's specified in that context file. So you've got just completely global defaults, like certain segment registers, certain flags, everything else is undefined, and then the context loader loads it up with memory with registers. And then for each emulation run, this context is duplicated and passed off to the emulation core. We're going to refer to these runs as emulation threads. Don't be fooled. It's not a multi-threaded application, but it's just convenient terminology. So each instruction is emulated as faithfully as possible. The arithmetic, in order of priority, first tries to preserve the destination as a pointer. If the operation can occur on the pointer such that the pointer can still be a pointer, the same base, different offset, then that's preferable. Secondarily, if the arithmetic is, the arithmetic will try to convert the destination to a pointer of the source's base. So like if you're doing arithmetic on, say, an integer as a destination and a pointer as a source, well, I mean, obviously the destination is not a pointer, it's a number. So we're going to try and convert it to a pointer of the source base first and foremost, just to try and preserve as much information as possible. Failing all that, it's just integer arithmetic on two integers with the non-determinism. So, there's special arithmetic to handle, each bit position 0, 1, or x. We do err on the side of non-determinism. So like if I had our, logic tables here to show you, they're just 3 by 3 instead of the usual 2 by 2, you got 0, 1, and x, and 0, 1, and x, kind of forming a matrix. And we do err on the side of non-determinism. So if we don't know what the outcome's going to be, we just jot down an x. Obviously, you AND anything by 0, it's going to be 0. You OR anything by 1, it's going to be 1. But, vice versa, you OR x by 0, and it's still going to be x because it hadn't changed. You don't know what's there. Arithmetic also modifies the E-flags register as the best it can according to the arithmetic as it's performed on the integer representations. You got some partially undefined integers, and you say add them together. Your carry flag might be undefined, auxiliary carry, parity flag. Any of those flags might be undefined depending on which bit positions are defined and undefined. But we try and do that to the best of our ability. However, sometimes faith just isn't enough. There's a lot of things that can cause a thread to end. The first and foremost being kind of emulated access violations. For instance, if you try and dereference a pointer out of bounds of the size of the memory region, that fails. If you try and write to a read-only region, that fails. Page permissions, in the case of pointer dereferences in the virtual address space, which of course corresponds to the snapshot, it looks at the page permissions. If you're violating something there, if you're accessing a missing page, that fails. Additionally, invalid opcodes, privileged instructions, and potential divide by zeros will all cause the emulation to fail. If you're dividing by a register that all the defined bits are 0, but there are some undefined bits, well, that register could be 0. It could cause a divide by 0. We don't know. We take it on the safe side because we're going for robustness here. Loops and branches. This is where undefined flags gets interesting. So first and foremost, we institute an instruction countdown to keep the emulation from running forever and to limit prohibitively costly, time expensive kind of emulation runs. We don't want this thing to run forever. We're using 100 as a reasonable default. Yuji, as Ryan mentioned, Yuji found a 91 instruction sequence, so we may ought to bump that up a little bit, but it is a reasonable default to start with. So if a conditional jump or a loop or conditional loop is reached with the requisite registers or flags undefined, and there's no way to tell which path it's going to take, we take both of them. What we do is we take the context at that moment, we copy it, we have the instruction count in each of those contexts so that you can't spiral out of control in like an indeterminate conditional jump to itself, for instance. And then the parent succeeds if both of the children paths were jotted down as successes. One path is the branch, one path is the fall through. If both of them result in execution or reaching your target buffer, then the parent is a success, and therefore the return address that led there, or that started that whole thing, is a success too. Yuji's also going to show that off. So if everything goes well, then it reaches your target buffer, and that return address is jotted down as a success. It's logged to the interface, and it goes on to the next one. Speaking of going on to the next one, I'm going to defer to Yuji now, who's going to give an awesome example using a vulnerability that he discovered. So here's Yuji.
Hi, good morning. I'm Yuji. Thank you. Okay. Okay, I will talk about the how to use the EE-RIP and the result of the performance of the EE-RIP. So, the first, we must flush the target process using the vulnerability to be exploited. And we should put the process as close as possible to the state that will be in effect when the execution is hijacked, like finished exploit with invalid return less like 41414141. I really like this value. And the process should definitely have a debugger on it with the first chance exception code. Okay, and I will show how to use the EE-RIP. And second, we must use the no, it's a psnap. Sorry. And we must use a psnap to grab the process memory snapshot. And this tool can identify the type of the data region, like a heap or stack or image or code or data. It's like this. And before starting the EE-RIP, we must create the context of the target process. And to create the context, we must study the environment at the crash time. It's like consistent pointers and integers and memory region of the interest. And if you want to double check your context, you can disassemble the code. And you must know that the context and the snapshot are both specific to the one version of the vulnerable process. Okay, and I will show the example context. And this is the context for the exploiting of the LSASS. It is for the Windows 2000 SP4. And I will show you how to create this context. So I want to see. Can you assist? Yep. Oops. Oops. Window's fucking shutting. Is it somewhere? Just a moment, please. Holy shit. What? Okay, so blank slide. Okay. Oops. All right. Okay, I will describe about how to create a context without this demonstration machine. Okay, and okay, oops. So we must set up the stack and registers and the buffer as the context. And the start address of the stack is the committed region of the thread stack. And the stack space is always aligned 64 kilobyte boundary, and but it move around. So we can assign the stack numerical value of like 0xxx000, like this. But it is totally separate outlet space. And we must set up the value of each registers. It's like EAX equals 0 and EBX equals 0 and ECX equals stack plus 5D38 or something. And this is the buffer, it's target buffer. And technically, you can execute the code anywhere in your buffer, But for the just simplicity, we choose to execute the code after ESP. Okay. We tested this EE-RIP against the following three kind of platforms. It's a Windows 2000 Advanced Server, it's English version. It's no service pack and no patch. And the Windows 2000 SP3 and SP4. And the target process is LSSS, and it contains the MSO 4011 vulnerability. It is basically a stack-based buffer overflow in the logging function, which we found. Okay, I will show you the result of the performance of EE-RIP. This is basically the completion with the commonly used return address finder. We just find the jump ESP and call ESP and push ESP and ret. And in case of the Windows 2000 SP4, the common used return address finder can just identify 167 return addresses, but the EE-RIP could identify the 824 return addresses. It's much better. Okay. And this is the distribution of the number of instructions from the start address to the target buffer. And this is what we found in Windows 2000 SP0. And what is my point? Okay. This is the table which shows the histogram and the number of the return addresses that will execute the code in the ESP, sorted by number of instructions required to get there. And the peak of the histogram is two instructions. That means that we found more 2 instruction sequences than any other number. And this is the longest sequence from the start address to the target buffer. And we import the limit of 100 instructions. So it's possible that there is a longer sequence could exist. Okay, this is in case of Windows 2000 SP3. The peak is 4 instructions, and the maximum number of instructions is 79. Okay, this is SP4. And the peak is 5 instructions, and the maximum number of instructions is 91. It's very long. Okay, and we found 7 return addresses exist on the Windows 2000 SP0 and 3 and 4. Like this. Okay, and I will show you an example of the return addresses. And this is the example return addresses for the SP4 with 27 instructions. Okay. And this example contains the undetermined branch, like, what's my pointer? Like this. And the EX is undetermined because it is loaded from the stack. So then the compare will make a zero flag undetermined. So the EE-RIP must test both directions. So yeah, I will show you the demonstration which use this address as a return address and try to exploit the LSAS. I have a Windows 2000 SP4 in the VMware. Oops. working? Ooh. Weird. It doesn't work. I don't know. Probably I cannot use. Okay, well, no. Okay. So I will crash it first. Oops. Weird. Oops. Like this, we got a first chance exception in LSA. And the yeah, this VMware doesn't work. P-snap? Oh, no, I don't have P-snap. Maybe. Huh? Oh, okay. Okay, I will talk about how to get the context. So yeah, this is a TIB, and the okay. This is the start address of the committed region of the thread stack. And the yeah, stack space is always aligned 64 kilobyte only, but it may move along. So yeah, we can assign this stack medical value as the you know, it includes undetermined value. And the weird, it cannot work. Yeah, okay, I will kill this one. Try to work. Oops.
It won't start?
Yeah, it didn't start.
Oh, wow.
Yeah, there is a kind of problem in the VMware, so.
Hey, work on that. I'll talk about what's to do. I'll talk about what's to do. You just work on that.
Okay. All right.
I'll get it. I'll get
So
it.
can
Well, I said if I spilled water on Yuji that, and that was all that went wrong, then that'd be a pretty good presentation. You got to allow for the unexpected. Let's see. So I'm going to go ahead and talk about what there is left to do on eReap. As somebody once said, you can't always get what you want, but if you try it out sometime, you just might find that it works good enough. No, I'm just kidding. There's always a way to make it better. Thanks for the courtesy laugh. Let's see. So first and foremost, the objective here is to use eReap to find a completely universal offset. The more universal, the better. The more versions it spans, the more languages it spans, operating systems it spans, the better. You know, I guess the holy grail would be an entirely universal offset across all Windows. Secondarily, it'd be nice to maintain the results of pointer arithmetic as a series of expressions. For instance, the example I've got here is kind of a hackneyed example, but it'll serve, is that if you take a pointer and you knot it, in the current engine, that becomes undefined, because let's say that pointer's base value is undefined. We don't know what virtual address it's at. Well, when you take you know, the inverse of that, then it is no longer a meaningful pointer. It's reduced to an integer, which is completely undefined. So then you add 1 to that, it's still undefined. Knot it again, still undefined. Whereas if we kept track of that as a series of expressions, then not pointer plus 1, not again, is going to actually equal pointer minus 1. So it's additional information that's kind of being lost during the you know, during the emulation. Another cool thing would be automated context reconnaissance. Instead of having a person have to sit there and say, hey, this register points to that, this memory contains that, is to have a program take multiple executions of this process, study what's there, you know, maybe even do things to intentionally kind of shake up the scenario, you know, to see what's really going to be constant and what's really going to be unpredictable. and just do all that in a third-party tool if you know, anybody's interested. And finally, it would be kind of nice to emulate exception handlers, because those contain cool function pointers that could be overwritten, and it wouldn't be that terribly hard to do, but we just don't do it yet. Can't get everything out in the 1.0, right? There would be some other cool things to do, such as supporting more instructions like MMX, and it'd be nice to have an indeterminate version of the BCD instructions like AAA or whatever. We don't have that now. You know, it takes into account undefined bits. It doesn't yet. And also to be able to contain a special value in the context, like to say, this register doesn't point to my target buffer, but it contains a value I'm interested in keeping around. So by the end of the simulation thread, that this buffer, or this value should still be accessible somewhere. That'd be kind of nice too, maybe useful in some circumstances. Let's see. I think that's about it. I'm going to see if Yuji is about ready to do the demonstration. Just a second. Looks like we're going to have that promised demonstration after all. It'll be just a second, so if y'all can resist the temptation of lunch, I'm hungry too. Let's just stick it out. Sweet, it's money. Can you hang on just a second, please? We'll get to questions, and is it cool? Y'all want to demonstrate now? Okay. Yeah, he's going to demonstrate right quick, and then we will gladly take questions and money.
Okay. So, okay, first I will put the breakpoint at the 7, 8, 5, 9, 9. Okay. This is that instruction, which contains 27 instruction one. Okay, and the yeah, we will send the exploit to this VMware machine. Oops. And return address is this one. Oops. Oh, yeah. So EIP is here, so I will do the step. Oh, it freeze. Oh, man. So, yeah, I attached LSSS, so it's been freezed. So, yeah. Sorry about that.
Hey, can you start the other, whatever.
Whatever.
All right. Cool. Thanks for your patience, everyone. We are actually going to, hold on a second. Here you go. We are actually going to take some questions now. Somebody in an EI shirt will be around to pick up your dollars, so just kidding. Let's go. Oh, okay, go ahead. We have considered abstractly emulating API calls. Generically, it could be as simple as just parsing the header file and saying, okay, the API accepts these arguments and passes back this kind of result. of course, just to gloss it over, it could just return like undefined values, and furthermore, you'd have to hope that no exceptions happen internal to the API or transfers of execution. But specifically emulating APIs, I can tell you how EEREAP does it. It just emulates right on into the API. It doesn't differentiate the boundaries of the API and any other code. It'll, with a sufficient counter, it'll keep emulating right on up to that int2e, and then it'll stop because it doesn't like interrupts. It doesn't know what they do to execution. Does that about answer your question? Okay, cool. Next up, go ahead. Oh, no, it hasn't. That particular protection is beyond the scope of what EEREAP is intended to do. I mean, and I guess people have proven if you can get around that protection, then this will provide all the return addresses that you might want to implement in your exploit. But we haven't tested on those versions of the operating systems yet, although there's theoretically no reason why it'd behave any differently. Next, Brave Soul. I saw you in the back first. Go ahead.
You're pointing out that some of these different versions that you tested against had different numbers of potential return addresses that you could use. Would you say there might be a goal to minimize the number that get generated, maybe a pilot or something like that?
Oh, you mean like a protection goal? Yeah. You could do that. It's really infeasible, I guess, to try and do restrictive things to your code. Definitely, it's not beyond the scope of possibility. But I think first and foremost, just keep people from being able to specify an arbitrary function pointer. And if you could, if there was one big universal address that you could disable by rebasing a DLL, then that'd be kind of effective in a subversive kind of way too. And in the front. Oh yeah, it'll emulate the code to the best. Oh no, we haven't. We ran it against LSASS. Yeah, it'll emulate the dereferences as long as the context is set up to initialize the memory and the registers to their proper values, which just kind of requires like a keen eye and looking into what's going on in the exploit. Dave. Well, first answer would be non-determinism. The CPU does not support non-deterministic values for the bits, so that alone was enough to necessitate emulation. Furthermore, the abstract memory regions and just undefined values, the context, and I pity the fool who sits there and just clicks the revert button in VMware. Next question. Anybody? Everybody hungry? Okay, go ahead. I meant to add that to the to-do list. Come up with no, I'm just kidding, no price list. Yeah, it'll be given away free. The emulation core is solid. We're still not happy with the way it displays the information, so we'll make it all snazzy and cool. But it will be up on the site. We should have a research portal upcoming shortly, and that'll be the place to get all the cool stuff. Okay. What, you want to do something? Oh, is that it?
I guess that's it.
Okay, thanks for everybody who stuck it out.